The hosting capacity has been calculated for different feeders. It was shown that the hosting capacity varies from 0 up to several megawatts for medium voltage feeder. In latter case, the hosting capacity is set by a loadability of feeder, not by over voltage limit. Although most feeders can host this significant amount of distributed generation, some tens of percent of maximum load. In some cases, the hosting capacity is very limited. Also, with future expected to increase. So, in this amount of distributed generation, a hosting capacity of some 10% may not be enough. So, in this session, a number of methods are discussed to improve this hosting capacity. So, we start with these classical methods and move on towards advanced and future methods. Among that is first one is new or stronger feeder. Adding more copper in the form of more or stronger lines will in the most all the cases results in higher hosting capacity. The dedicated feeder in case of large unit connected to a weaker part of grids are commonly used as a solution. Building a completely new feeder in many cases in the form of underground cable could be easier than strengthening the existing feeder. Over voltage might still occur, but because it is a dedicated feeder, only a generator unit is exposed to the over voltage. However, this can be fully considered during the design of feeders and the generator unit. Additional advantage of dedicated feeder is that it can be designed to prevent any overloading. The solution is however practical only for larger unit. For a smaller unit, the cost of new feeder will be too high compared to the total cost of unit. Also, the cost of new feeder will be highest when the generator is located further away from the main medium voltage substations. So these are exactly the location where the risk of over voltage is highest. So rewiring the feeder or the part of feeder with a thick wire will be cheaper than building completely a new feeder. So it will be also easier to obtain a permission for rewiring and existing feeder than building new one, overhead line feeder. So rewiring however cause rather long planned interruptions for existing customers. The impact of feeder section on hosting capacity is not big as what we would expect. So here the lower cross section result in the lower voltage drop during low load. So this partly compensates the increase in the hosting capacity due to the lower resistance. However, by using sufficiently thick wires, there is no need for second voltage boosting. This has a main impact on hosting capacity. Network operators in several countries are replacing this overhead line with cable from the voltage control viewpoint. So the cable can be seen that as a line is which is partially series compensated. That a series reactance of underground cable is less than that of overhead line. The voltage drop along underground cable is therefore less than along this overhead line for some cross sections also. So this will reduce the need of voltage boosting, which gives an increase in hosting capacity. So replacing line with the cables with the same cross section without any further means might however reduce this hosting capacity. The voltage drop during minimum load, which is partly due to the reactive power demand, becomes less, whereas voltage rise due to the distribution generator remains same. So thus there is less generation needed to reach the over voltage limit. Building new rural distribution network completely based on cable might even result in significant reduction in the hosting capacity. Lesser the voltage drop per unit length, which allows the longer feeders with boosting point located further away from the main substations. The minimum over voltage margin is independent of feeder. So with the cables with the point will further out along this feeder where the source resistance is higher, so thus the hosting capacity will become small. The hosting capacity is also increased by shortening the feeder. So the main cost associated with this is more transformer and more substations are needed. This is about new or stronger feeder. So let us move on to the alternative method for voltage control. So let us see the alternative method for voltage control. The various calculations in these sessions that have been shown that one of the main limitation to the hosting capacity is that the fact of voltage boosting used, which is independent of load. The load dependent boosting method would be able to increase the voltage during high load, while which does not have any impact of the voltage during low load. The line drop compensation scheme is the first step in the right direction. However, the disadvantage of this scheme is that it assumes all the feeder from the same HV and MV transformer to have a similar load pattern. So when adding the large generator unit to the feeder, this is no longer holds. So the line drop compensation used for this voltage control with a large wind park that is connected to 230 volts kV, where the point of connection is 75 kilometers from the wind park substation. The relay uses a input not only the total current through the transformer but also the current from the main bus into the feeder with the distributed generation. From the difference between the feeders and the knowledge on historical load profile, the amount of generation is estimated. So this is used to calculate a correction term for a line drop compensator. A successful field trial of relay in 11 kV network with 13 feeder and 5 megawatt wind power connected to the one of the feeder, which is both the shunt and series compensation, has been discussed. So here the concentrated series and shunt compensation is more effective, where which is located nearer so to at the start of feeder, as it compensate only the voltage drop due to downstream load. But this results in higher voltage magnitude at the start of feeder as and when the compensate starts. So when this drop is substantial, part of total voltage drop, a series compensation is suitable option. So in feeder with small cross section, the voltage drop is mainly due to active power and series compensation. The shunt compensation is more effective when it is connected at the end of the feeder. A switching scheme is needed to prevent the voltages. To prevent excessive switching, a large hysteresis is preferred. A static power compensator scheme or fixed capacitor scheme with a regulated shunt reactor could be an alternative for this, which may result in small voltage magnitude variation along feeder. Another possible solution is that installation of a reactor on a secondary side of distribution transformer. When the voltage magnitude exceeds the threshold, the reactor is switched on and its reactive power consumption results in the voltage drop. Some of the alternative method for voltage control. So let us see the accurate measurement of voltage magnitude variation. Distribution network operates in many cases do not have detailed information about voltage magnitude which are experienced by their customers. During the design, an estimation is made of after diversity maximum demand. On the basis of this, a minimum feeder cross section and maximum feeder length are determined. So this approach has shown us a result in an acceptable voltage for various customers. Adding distributed generation will in long term requires a new design method, for example, which is based on estimation of this after diversity minimum consumption and after diversity maximum production. In a short term, the distributed generation will be added to the existing feeder, the design in the classical way. The hosting capacity of such feeders is determined by over voltage margin which are experienced by individual customers. So this value is however often not known to the network operator and will have to be estimated. To prevent the excessive overvoltage and possible complaints and penalties, the overvoltage margin is underestimated, resulting in low or even sometimes a zero hosting capacity. An accurate measurement of overvoltage margin for an individual customers will make it possible to determine the hosting capacity more accurately. So this strongly reduces the risk of unexpected overvoltage. It's also in most cases will allow more distributed generation to be connected to the feeder. The automatic metering equipment that's been introduced in many countries is often able to measure the voltage magnitude with a time resolution. For example, consider that although not perfect, it will give sufficient information to provide an accurate estimate of this hosting capacity. By obtaining more accurate information on actual voltage experienced by customers, so network operators will be able to allow more distributed generation to be connected without the risk of unacceptable over voltage for other customers. Those some measurements at the same time gives the network operator some information about available under voltage margin for future load growth. So this is important information for planning future investment in our distribution network. So this is about an accurate measurement of voltage magnitude variation. Let us move on to allowing the higher or over voltage. The design of distribution feeder is based on over voltage limit and under voltage limit. The traditional trade-off between the range of voltage magnitude and maximum length of feeder. With higher over voltage and lower under voltage, the longer feeder length would be possible. The saving achieved by allowing longer feeder is especially in reduction in the number of transformer stations. The longer the lower voltage feeders are, so the less distribution transformers are needed. So longer medium voltage feeders requires HVMV transformer. So the relation is more or less a square. The number requires 78% more transformer station. So with a distributed generation, higher voltage and lower under voltage, so could impact the lower voltage under voltage limits. So this allows the deadband of tap changes controller to be shifted, which reduces the need of voltage boosting. So as discussed previously, the greatly increasing the hosting capacity should also be noted that higher permissible voltage and under voltage could be used by network operators to build the feeders. This would most likely to reduce the hosting capacity because the location with lowest over voltage margin would further out along the feeder, allowing higher over voltage and lower under voltage would thus not automatically result in more distributed generation being able to connect to a feeder. The choice of over voltage and under voltage limits remains a sensitive issue, as many recent discussions between the network operators and equipment manufacturers and also regulators have been done regarding this. A well-defined and strict voltage characteristics are important for any network operators for to limit this over voltage. So with this the following discussion, so I conclude the allowing of higher voltage or over voltage. So let us see the next point, that is a risk-based approach to the over voltage. It is shown that the hosting capacity can be increased significantly by allowing the over voltage limit to be exceeded for a small percentage of time. Such an approach is especially effective for sources having a strongly intermittent character, such as solar power and wind power. For a more constant source like CHP, and a risk-based approach will be less effective. The percentage during which the over voltage limit can exceed was taken equal to 0.01% and 0.1% and 1%. The discussion what is an acceptable percent is the probability even more difficult that discussion on what suitable over voltage limit. Both discussion come back to one primary aim of the power system: to supply the equipment with suitable voltage magnitude. The risk based approach should be discussed. To supply the equipment with suitable voltage magnitude, so the risk based approach which has been discussed previously, in fact not fully completely. So what should be considered is not a probability that an over voltage limit is exceeded, but the probability that equipment is damaged due to over voltage. So this probability is most likely to be smaller, especially as one takes into the consideration also but the probability of equipment that is damaged due to over voltages, so this probability is most likely to be smaller, especially as one takes into the consideration of high voltage magnitude that occurs during low load when the less equipments are connected to the network. So what needs to be considered is the probability that those customers experiencing high voltage have sensitive equipments that are connected to in which high voltage will occur. A discussion on the use of risk-based approach should again involve all the stakeholders, where an important point of discussion should be who actually carry this risk. If network operators get a fine when over voltage limit is exceeded, a worst case approach using the safety margin will likely to be used. When a fund is created to pay the damage for equipment due to over voltage caused by the distribution generation, so this will encourage the network operator to allow more distributed generation to be connected. The great unknown in the discussion of permissible voltage is that immunity of the equipment for over voltage. Although the value of 110% of nominal is often mentioned, so there are a number of studies confirming that the equipment starts to experience damage when the voltage slightly exceeds this limit. On the other hand, the customers complaining about the damage of equipment often turn out to be an expensive due to this high voltage magnitude. The most sensitive piece of equipment appears to be an incandescent lamp. In modern type of lighting, so these are less sensitive to the over voltage. Although there are not detailed studies, so to confirm this, before completing risk-based approach can be implemented, the equipment manufacturer, standardized setting organization, and regulators have to get involved in this discussion. Risk-based approach is not simple and may require a significant effort before it can widely used. However, it has a potential usually to increase the amount of distributed generation that can be connected without any additional investment in the distribution network. So another barrier used in the risk-based approach is that the way in which general public expects the companies to ensure the risk-free environment. It is sometimes suffers for a company to perform a domestic study using this worst case limit, then consequentially accept a small but non-zero risk. Removing this barrier again requires an industry-wide approach in which risk is based on the approaches will become accepted as good for a power engineer practice. So this is again not an easy task. So with this, these are some of the risk-based approaches in over voltages. Let us see over voltage protection. What are the protection done for this over voltage? Tripping up of distributed generator when a terminal voltage comes very close to the over voltage limit is a very effective way of preventing over voltage. So there are a number of advantages with such an approach. The protection threshold can be set close to the voltage characteristics, that is actual maximum voltage allowed on a network. The generator needs only to be tripped when voltage gets too high for the customers. Instead of planning level, a value close to the voltage characteristics is used. So when unit size exceeds the hosting capacity based on the planning level, so actual instance where the tripping needed may be very limited in the number or not even occur at all. The unit tripped only when the voltage is high. This is during the period of low consumption and at the same time high production. The amount of energy produced by the unit is not influenced by the estimations on a maximum voltage drop or maximum production. So this is obviously a huge gain compared to the setting a maximum production limit, which is based on the worst case scenario. The method is very easy to implement with none or very limited extra investment are needed here. So with needed what is needed is the voltage measurement, a simple relay and a breaker. So with a long delay could also result in the significant losses of the production. So whenever over voltage occurs regularly for a shorter period, some generation units may not be easy to start and stop. For wind power and solar power, starting and stopping is a serious concern. But for CHP unit, this could be inconvenient. Stopping electricity production may also require the stopping the heating production. So both are correlated here. So when the heat is produced used in the industrial process, the economic consequences could be very severe. So the disconnection and reconnection can result in the significant voltage steps where the large amount of generations are involved. A spread in the voltage threshold and the spread in the reconnection time could be used to make a transition smoother with large penetration of this solar power distribution network. So this will trip due to over voltage again, which becomes a common phenomena. So this would result in a serious tripping. So could also around noon for every sunny day. So reduction in the amount of energy generated by this it is not a feasible solution. So the curtailed energy would therefore be a much higher percentage than the percentage of time that is available to generate. So this is about over voltage protection and some of the techniques that are available for over voltage protection. Let us move on to the over voltage curtailment. Okay, in over voltage curtailment, a curtailment scheme in which the production is reduced more when the voltage get closer to the limit is more efficient scheme. So this will result in less loss of production than the over voltage protection, but some stability concern remains. The impact of over voltage tripping on the voltage and on the energy production is illustrated in this figure. You can see here. So the difference between the solid curve and the dashed curve is proportional to the amount of power that is tripped. This implies that the area between the two curves is proportional to the energy, not produced. In a case of wind power, this would be spilled wind. The maximum possible amount of production at any moment in one would result in voltage exactly equal to the over voltage limit. This is shown in a dotted line in the figure. The area between the dotted line and the solid line curve is necessary energy lost, where the area between the dotted line and dashed curve is the unnecessary energy lost. The perfect curtailment algorithm would keep the voltage exactly at a dotted line and make use of power system to transport a renewable energy as much as possible. Such an algorithm does not exist yet, but number of algorithms are being discussed in the literature survey of many paper, and no doubt they may develop. So in this section we will discuss some of the property of curtailment algorithm and make a reference method that been presented in literature survey of many paper will conclude here. A possible method of a power curtailment is shown here in the next graph here. So only local measurement parameters, so there is no communication between generation unit or central controller needed. So whenever the voltage point connection exceeds the value U reference, so the power production will be limited. The second voltage threshold U max, where the power generation could be reduced to 0. So here the power generation equation can be given by, so P generation is equals to P reference to the P max 0, that is 1 is to beta to the U minus U reference. There are some limit to the reference where U is less than U reference, so U is between U reference and U maximum, or U is greater than the U maximum, where beta is equals to 1 divided by U max to the U reference. So the principle of voltage control is shown in the figure, where dashed indicates that rise in the voltage. These are the thing is talking about. The dash indicates the rise in the voltage level. So moving on. U is equals to U naught plus R into power generation. So this is the formula for principle of voltage control. So where you can see that for maximum production, here it is again assumed that there is no exchange of reactive power between generator and grid. So the level of consumption is represented by U naught for a situation without generation. So in the figure, in the previous figure what we have seen, U naught is a point of intersection with the horizontal axis. So in the intersection with the horizontal line, P gen is equals to P max. This is a voltage for a maximum production, that is U is equals to U naught plus RP max. So by operating point, if I combine above two equation, so I will get this following relation: U minus U ref is equals to U naught minus U ref plus RP maximum to the 1 plus beta RP maximum. Here the denominator gives the voltage rise above the reference voltage, as it would be in without curtailment. The curtailment reduces this voltage rise by a factor 1 plus beta RP maximum. The production limit will be equal to U minus gen limit, so P max U max minus U naught, so to the U max minus U ref plus RP max. So for example, during one course of day, no generation, the voltage U naught moves up and down. So the voltage with distribution generation is curtailed whenever it rises above U reference. So the maximum voltage U max will not be exceeded as long as there is no exceeded by no generation voltage. So the resulting voltage variations are shown in our previous graphs we have seen. The comparison shows that curtailment needed for tripping with significantly increase in the amount of energy produced. Maximum voltage is never reached in this case because no generation voltage remains below over voltage limitations. So the above expression for voltage and production limit have been derived for one large unit which is connected to the feeder. However, it can be shown easily that the expression also holds for more units which are connected at the same location. So in this case, Pgen and Pmax are the sum of the values for individual generators. The curtailment of individual generator is by the ratio of their maximum production. For example, in the above equation, if we use, it will produce some reduced result by 25% of total production. So each unit would be reduced by 25% compared to maximum production. So this assumes that each generator produces exactly the amount to which it is curtailed. Some unit may not be able to curtail the production, and it will instead trip completely. A remaining unit will reduce the production by the somewhat smaller amount. When multiple units are connected at a different location, the curtailment is still shared, but no longer in proportion to the unit size. Instead, the local no generation voltage and local source resistance impact the sharing. So this is still possible to obtain closed expression for resulting voltages and production limit, but those are complicated expression and do not give much additional information instead. So the two examples are given here.